Hello, everyone, and thank you for joining the presentation. My name is Walter Gonzalez. I am the Group Test Manager for the Electrical Safety Engineering Division here at ETAP, and I'm involved in generating specifications, the testing and validation, and providing technical support for electrical safety products with an emphasis in short circuit and arc flash analysis within ETAP. Today, I'm here to talk to you about an arc flash mitigation technique referred to as energy reducing line side isolation equipment. To do that, we're going to go ahead and explore what are all the different locations within a piece of equipment at which an arc flash event can take place. And we're going to do this in order to help identify which of those locations tends to be the most hazardous. After doing so, we'll talk about the different mitigation technologies that we can consider to help reduce the amount of incident energy exposure for these different hazardous locations. Then we're going to go ahead and talk in detail about one of those technologies, which is energy reducing line side isolation equipment, by talking about one example of the technology, which is Schneider Electric's ArcBlok. Then we'll go ahead and do a demonstration using ETAP to see how we can model energy reducing line side isolation equipment, such as ArcBlok, when running arc flash analysis. Now, on the next slide, what you see is a physical representation of a switchboard and all of the different locations at which a arc flash analysis can take place. Zone 1, Zone 2, Zone 3, Zone 4, so on and so forth. Now, when I'm talking about Zone 1, you can see here in this pink area, this is referring to what we typically talk about in the industry as a line side arcing fault, which is a fault on the incoming line side conductors for this main breaker. Zone 2 would be a bus arcing fault. And let's say we were to have a load protected device right below this bus here, then this would be Zone 3. And let's say we want to take it even further downstream, we can also look at a fault at the load terminals of a motor, for example. Now, all of these different zones you can model within the ETAP software, where you can actually perform the arc flash analysis at each and every one of these locations, so you can quantify the hazard level associated with each section of the equipment. Now, although ETAP can model those details, today what we're going to do is we're going to focus on zones 2 and zones 1, which are going to be some of the more challenging locations to deal with because of the higher amounts of incident energy exposure that you can have at these locations. And the reason why I reached this conclusion is, of course, in the power system, the design always takes into consideration protection of the equipment and the selectivity of the protected devices. In other words, the further downstream I am from Zone 2, the faster the protected devices are expected to be, right? My load protected device, let's say right below Zone 2, would definitely have to be faster than the protected device protecting the bus arcing fault, which is that main circuit breaker. And that's true because we want to maintain selective coordination. I want to make sure the protected device closest to the fault is the one that's going to go ahead and clear the fault instead of waiting for a further upstream protected device, right? Now, in this particular example, what we did is we went ahead and did a arc flash analysis for Zone 1 and Zone 2 using typical data and typical characteristics of protected devices such as breakers and fuses. Now, in this particular case, when we did the analysis, what we saw is for the bus arcing fault, we estimated 1.6 calories. However, for the pink zone or the line side arcing fault, we estimated 15.6 calories per centimeter squared. Now, the reason why the difference in the energy is so drastic is because of how long the arc was allowed to persist for. So, for example, for the bus arcing fault, we're able to take credit for the circuit breaker that's just directly upstream to clear that fault. However, if a fault were to happen on the line side conductors of the breaker, of course, cannot clear its own fault. Therefore, we have to look further upstream, which in this case is going to be a upstream fuse. Now, that fuse, of course, is going to be slower than the circuit breaker, leading to a longer clearing time and leading to a higher amount of incident energy being released. Okay, so this trend you're going to actually see in simple systems like this radio system we just looked now, or even in more complex systems, because the bottom line is in these line side arcing faults, we do have to rely on protected devices that are further upstream, which are going to be typically slower than downstream protected devices. Now, to address this, we need to consider arc flash mitigation techniques. So on this PowerPoint slide, what I've done is I've summarized some of the more typical and popular mitigation techniques. Again, this is not a comprehensive list. It's some of the most popular techniques out there. Now, one thing you're going to notice as we talk about these different mitigation techniques is the main goal for most of these techniques is to reduce the amount of clearing time, or in other words, reduce how long we allow for that arc flash event to persist for. Okay. For example, when we're looking at the first case, which is differential relaying, we have a high-level depiction of the protection scheme here, where you see we have multiple set of multiple CTs monitoring a certain portion of the power system or a zone of protection, where we monitor the current coming into the zone and leaving the zone of protection. And if a mismatch were to occur with those two different sets of currents, then the differential relay is noticing that there's an abnormal condition there. In other words, a bolted fault or an arcing fault condition, where the differential relay will then send a trip signal to a upstream protective device, such as a circuit breaker. And in that particular case, the reason why the differential relay is going to be one of the more popular techniques is because its response time is significantly faster than that of overcurrent protection that would come, for example, from a fuse or from a relay with overcurrent protection settings and breaker combination. Now, similarly, if you look at arc flash relays, what they do is they monitor certain sections of the equipment and they check typically for two conditions, an abnormal amount of light and an abnormal amount of current within the actual electrical system. So when those two conditions are detected, the unit knows that an arc flash event is taking place and it sends a quick trip signal to an upstream protective device. And again, this technology is going to be significantly faster than your typical overcurrent protective devices. Now, that's not to say that overcurrent protection can't achieve similar goals. We can also look at technologies or protection schemes like zone selective interlocking that does use overcurrent protection to help mitigate incident energy releases, the amount of incident energy released. So for example, let's say we were to have a fault at this location here, this red breaker and the upstream breaker, when you're looking at a zone selective interlocking protective scheme, does two things. One, the breakers themselves have two sets of trip curves, one being the traditional overcurrent trip curves, and then a second set of trip curves, which are based on zone selective interlocking protection schemes. And those ZSI or zone selective interlocking protection scheme curves are typically much faster. So if the fault were to happen in this particular location, what happens is this breaker sends a signal to the upstream protective device telling it to apply an intentional delay to allow for this protective device, which is closest to the fault, to clear that fault by using its zone selective interlocking trip curve, which again is going to be significantly faster than the typical overcurrent characteristics that it has. So what this basically does is it allows two goals to be achieved. One, we maintain selectivity because we're not triggering a protective device to be significantly faster than those that are downstream or upstream from the protective device. And in addition to that, we're also engaging a faster trip curve, helping us reduce that clearing time for the arcing fault. And in addition to this, you can also consider other technologies such as the current limiting circuit breakers or current limiting fuses. Now, with these protective devices, once the amount of current that these protective devices exceed a certain threshold specified by the manufacturer, what they do is they limit the amount of current that's going to flow out of that protective device to the rest of the system. And it also clears the fault significantly faster than your typical overcurrent characteristics would. Now, the reason why that's so important to keep in mind is because it's not as easy as, adding current limiting protective devices throughout your facility. It's a lot. You have to basically make sure that the protective devices will operate within that region to be able to take advantage for those two benefits that I discussed earlier. Now, these mitigation techniques that we've discussed so far, differential relaying, arc flash relays, zone selective interlocking, current limiting protected devices, these are all examples of devices or mitigation techniques that can be configured to reduce the incident energy release for line side arcing faults. However, you have to be very careful when choosing mitigation techniques because that's not always the case. And I'll show you an example of that next. For example, let's go back to the very beginning of the PowerPoint where we talked about that simple radio system with on the right-hand side of this figure. On the left-hand side, what I have is a low voltage circuit breaker that has the ability to engage maintenance mode. Now, if you don't know what maintenance mode is, this is basically a switch that engages a temporary trip curve for this circuit breaker, which is significantly faster than its typical overcurrent characteristics. Now, when we gauge that trip curve, what we basically do is we introduce selectivity issues. For example, because we introduce this temporary trip curve, of course, we violate the selectivity or coordination of the system for any downstream breakers. But we do that, we sacrifice that selectivity to maintain the incident energy at the bus arcing fault to be less than a certain threshold, right? The only problem with this particular setup of the maintenance mode, as you can see here, the maintenance mode is only applied by this breaker. If we were to have a line side arcing fault, even with this maintenance mode option enabled for the breaker, we're still back to square one for the line side arcing fault because we have to rely on the further upstream protected device. So the reason why I bring up this example is this is key when you have to decide what mitigation technique can I consider, let's say if the line side fault is in fact the most hazardous location, which is what typically happens, right? So the main takeaway from the slide that I want to provide to you guys is there's three criteria to consider when choosing a mitigation technique. One, of course, are going to be economics. Which of these mitigation techniques is most expensive? Which one does my budget allow for? Second is going to be, can this mitigation technique be used for line side arcing faults, right? Just like this particular case, introducing maintenance mode perhaps help me reduce energy at zone 2, but it won't help me for zone 1. And then the third thing is, can this mitigation technique be, for example, in an existing line that be retrofitted to my equipment? Or is that another constraint that I have to work with where perhaps I may not be able to consider some of these mitigation techniques? So again, these are all kind of things to check off on your list when helping you determine which mitigation technique you can actually consider to help reduce the energy exposures for those line side arcing faults. Now, another technology to consider is the energy reducing line side isolation. Now, this equipment basically is going to be equipment that encloses the line side conductors so you can't interact with them, and it also isolates the conductors themselves, as seen here on the right, to reduce the likeliness of the line side event taking place. So the idea behind this, of course, is if the electrician working on the equipment can't interact with the line side conductors, the likeliness of that line side event taking place has been reduced. Now, one thing to consider, however, though, is if there is some sort of a condition where that line side arc does eventually actually take place underneath those covers, we need some sort of a way to address that, right? Some technologies that fall under the energy reducing line side isolation unfortunately stop at just reducing the likeliness of the arcing event taking place. They didn't address the second issue at hand, which is what were to happen if the line side event does take place. However, there are comprehensive technologies that do address both concerns. And one example of that is Schneider Electric's ArcBlok technology. Now, Schneider Electric's ArcBlok technology starts off with isolating those line side conductors, just like we talked about earlier with this, for example, protective shell, as you see here in yellow, where we cannot interact with the line side conductors. And then underneath those conductors, we also have some isolation between the actual conductors. But the added benefit of ArcBlok is ArcBlok goes one step further. if a arcing event does take place, the equipment is actually monitoring the line side conductors, and the moment that it detects that a line side arcing event has taken place, it uses circuit breaker interrupting technology to help stretch that arc and extinguish it in less than one cycle. Now, because it does this so rapidly, the amount of energy that's released for that line side arcing event has been tested and found to be less than 1.2 calories per centimeter squared. So, in addition to this, it's always the interruption of the actual arc is done passively. And when Schneider Electric refers to this being done passively, what this means is that there's no circuit breaker being triggered to clear the fault. So when this is done passively, the beauty of it is that there's no interference or any influence in the coordination of the system. We're not introducing miscoordination like we did with maintenance mode, for example, because we're doing this passively. So again, the main takeaways from the technology is that the likeliness of the line side arcing fault is reduced. If the event does take place on the line side connectors, the event is basically extinguished in less than one cycle with an exposure less than 1.2 calories. And third, this technology does not interfere or influence the system coordination in any way. Okay. And the equipment itself can also be added to both new and existing equipment. So that's another added benefit as well. Now, what we're going to look at in this next slide is going to be a video of a test that was done for a traditional MCC and a MCC with ArcBlok incorporated. Now, I'm not going to go into details about how long the arc event was allowed to sustain in the traditional MCC, how much fault current, how much energy was released. And the reason is because the gist of it, again, of what we're talking about is we know line side arcing events are typically the most hazardous locations, whether that be a 25 calorie release, a 40 calorie release, it's hazardous, right? So we want to see graphically what that would look like for the MCC versus what you would expect out of an MCC with ArcBlok integrated. So let's go ahead and take a look at that. So let me rewind that really quickly. As you can see here, when the arcing event takes place, you'll see that there's a large amount of instant energy that's going to be released. And not only that, but you actually have pieces of the equipment being ejected. Of course, if some bystander were to be walking by, this is definitely hazardous, right? They might not even be aware that an internal arcing event is happening and you're going to be exposed to these different things. They may not even have the appropriate PPE, right? So not only that, but of course, imagine the damage that's happening to the equipment internally as that event is taking place. So now we're going to go ahead and switch to the rest of the video clip to see what kind of a response we get for the MCC with ArcBlok installed. So as you can see there in that video, in this part of the video, when the line side event takes place on the equipment with ArcBlok, it's so minimal compared to the traditional MCC, and we're going to see it side by side next again. So because ArcBlok is able to detect that arcing fault on the line side conductors and extinguish it so rapidly, we can actually see that the amount of energy exposure and the damage to the equipment is significantly smaller than that of the traditional MCC on the left-hand side. So now what we're going to go ahead and do is we're going to go ahead and switch to the latest revision of ETAP to see how we can model technology like ArcBlok when running an arc flash analysis.
So here what we have on the screen is the latest version of ETAP, where we're going to run an arc flash analysis on this example project where the facility has multiple MCC lineups being fed by different size transformers. And our first goal is to identify how much of a difference we have between the incoming line side arcing fault and the bus arcing fault. To do that, We're going to go ahead and run ArcFlash by selecting the ArcFlash mode and run ArcFlash using the yellow triangle on the calculation toolbar on the right. Now, what I'm going to call this first initial ArcFlash report is ArcFlash underscore as found. And this is to signify that I'm running the evaluation with the existing settings and library data for each of the protected devices that have been chosen based on typical protection and coordination guidelines. Now, once the calculation loads, as you can see here, we can see that all the annotations on the bottom right here belong to the bus bars. The reason why I know that is when you move and highlight the annotation, it highlights the bus. And then the higher annotations are going to be the annotations belonging to the line side arcing faults. So as you can see here, drastic differences. The energies at the bus bars across the different MCCs are in the range of no more than 3 calories, but for the incoming line side arcing faults, the energy is drastically larger and in some cases higher than 100 calories. So here, of course, we have to start thinking what exactly is going on, which again brings us to what we have seen already in the previous part of the presentation, right? The most likely reason that we have that high release of energy is because of the response time of the upstream protected device. We can quickly confirm that's the case by opening the ArcFlash analyzer. And when doing so, if you've never used the ArcFlash analyzer, this is basically an interface where you get a summary of all of the ArcFlash input data and calculation results from the simulation. So for example, let me go ahead and identify using the ID column. I'm going to go ahead and look for the arcing location, the source PD line side arcing location, which is nothing more than the line side arcing fault. What I do there is I simply select the total incident energy result here and hit the one line diagram icon. When doing so, I'm going to get an animation on the one line that shows me what happens for a fault on the main incoming circuit breaker. And as expected, the first upstream protected device clears the fault, but due to protection and coordination criteria, the response time of that fuse is significantly slower, leading to a higher release of incident energy. And as you notice here, what ETAP calculated is about 2.9 seconds of clearing time. However, what we have here in the analyzer is listed as 2 seconds. The reason why we have that difference is because for the calculation, I've gone ahead and limited the clearing times to be no longer than 2 seconds based on the typical rule of thumb used by many engineers running ArcFlash studies, which originates from the NFPA 70E, depicting the expected amount of time it takes for somebody to react when exposed to a arcing fault. Now, of course, that has its own constraints and assumptions, but that's the reason why I'm basically using that criteria to limit the incident energy to be calculated at a clearing time no larger than 2 seconds. But even by doing that, I still have a large amount of incident energy that I'm considering here. So the only thing I can do now is start considering mitigation techniques. So here, what I'm going to do is I'm going to assume that I've done my due diligence and I've gone to the conclusion that ArcBlok or energy reducing line side isolation equipment is going to be the best mitigation technique for this particular facility. So to model that, what I'm going to do is I'm going to go ahead and hit close on the ArcFlash analyzer. I'm going to go into my bus bar. I'm going to go into the rating tab of that same editor, and then I'm going to launch what I call the enclosure editor. Now, the enclosure editor, if you're not already familiar with this, is basically an interface where you can define all of the ArcFlash input data for each and every location within the MCC or a switchgear where you want to run an ArcFlash analysis. So what I need to do here is I need to identify which location needs to consider that energy reducing line side isolation equipment, which in my case is going to be for a line side arcing fault, where that is going to be defined in the enclosure for the main incoming circuit breaker. So that for me is row 25. So in row 25, what I'm going to do is identify the enclosure isolation column, and I'm going to change its current status to energy reducing line side isolation. Next, I'm going to go into the parameters tab. Using the same row once again, I'm going to go into a column called user defined incident energy, as seen here. And this is where I basically specify and tell ETAP if the energy reducing line side equipment is installed, what is the maximum incident energy I expect to be released for a line side arcing fault? Based on this example with ArcBlok has been tested and found to release less than 1.2 calories, hence why I have entered 1.2 calories here. Okay. Now, of course, this change has to be applied everywhere ArcBlok is relevant. So, for example, I'm going to have to repeat that process for each of the main incoming circuit breakers. However, I've done that ahead of time in the interest of time. So that is now applied to all of the main incoming circuit breakers. Now, the last step I have left is to go into my study case and simply go into incident energy. And now what I'm going to do is I'm going to enable this option called consider incident energy for reducing line side isolation. This basically enables the consideration for that energy reducing line side isolation option that I've selected for each of the line side arcing fault locations. So I'm going to go ahead and click OK. And then what I'm going to do is I'm going to change this to prompt. And I'm going to go ahead and rerun ArcFlash by specifying a new report name called ArcFlash_ with ArcBlok. Now, when doing that, now it's going to go ahead and examine each location where ArcBlok is considered and limit the incident energy based on the criteria that I specified in the enclosure editor. So as seen here, the energy at these different line side arcing faults is now limited to 1.2 calories, and we also have a green symbol that appears on the one-line diagram letting us know there's something special about this location. And there's also text there letting me know what exactly is special about the location. So as you can see right there, what I have abbreviated is energy reducing line side isolation is installed, hence the limited incident energy. Now, if you ever want to modify that text, you can simply go to your tools, options, preferences, and you'll notice under the ArcFlash section, there's something called incident energy reducing line side user-defined text. Okay. Now, what you're going to do here is you're simply going to specify the type or name that you want to specify for the user-defined text. Let's say you want to be a little more specific. Since we're using ArcBlok at this facility, what I can type is ArcBlok installed. So I'm going to go ahead and click OK. Here, you can see that by changing that text, everywhere that I'm considering ArcBlok across the one-line diagram, I can see that we have the symbol showing up, and we also see that we are notified that ArcBlok is being considered for these different fault locations. Okay, so that's another indication of the consideration for a mitigation technique. And additionally, if you do, for whatever reason, do not notice those symbols on the one-line diagram, if you go into your ArcFlash analyzer, and let's say that we were to look at the reports that we just generated, right? So right now, the analyzer itself, as you can see on the left-hand side, is looking at two different reports, and the results it's comparing is the total incident energy. And as you can see here in the first 13 rows, the location is the bus arcing fault locations, which of course have seen no change from the introduction of ArcBlok as expected, right? Since it is a mitigation technique for line side arcing faults. However, if you go into rows 14 and lower, which are the line side arcing faults, you can see that we went from drastically high incident energy values to 1.2 calories based on ArcBlok. Now, if I were to go ahead and examine only the report for ArcBlok, I wanted to also show you that on the right-hand side, we have a column called Effect of Main Protected Device Isolation on FCT, where we typically identify any main protected device isolation issues. For example, if you look at a piece of equipment where perhaps the isolation doesn't allow you to take credit for the first upstream protected device, this is the column that would usually flag that. But we also use that same column to identify any location that's considering the energy reducing line side equipment as seen here, which is being flagged for all of the different main breakers for those MCC lineups. Now, using this criteria here, again, is a second confirmation, just letting you know, hey, we're considering energy reducing line side isolation equipment. please confirm that this was the intent of the modeling you have done, right? So there's multiple checks and balances in there to make sure that we can identify and apply that type of mitigation only where relevant, okay? So now that pretty much wraps up what we wanted to go ahead and model within ETAP. And again, just to summarize what we've talked about today, based on the analysis we've done of all of the different arcing fault locations, it's evident that one of the most hazardous and high energy exposure locations are going to be line side arcing faults. The second item that we concluded is that when choosing incident energy mitigation techniques, it's key to identify that the mitigation techniques should also be applicable to line side arcing faults. Two, you need to check if there's something that you can apply to an existing lineup, if that's the case you're dealing with. And third, of course, is to make sure that how do the economics of this mitigation technology work? Is there something that are one of these choices a better fit for the budget I'm working with? And then lastly, based on this demonstration that we just did now, we were able to see that to model technologies such as energy reducing line side isolation equipment, or in this particular example, ArcBlok, we just need to make a few simple changes to the ETAP project to go ahead and model and take credit for that mitigation technique. And keep in mind, one thing I also want to mention is we can only take credit for that mitigation technique as long as the equipment is being operated under manufacturer specifications, right? We want to make sure that the covers are on and they're not being tampered with. The moment we start messing with the covers and are operating that equipment something other than what the manufacturer has recommended, of course, we cannot take credit for that energy reducing capability of the equipment. So do keep that in mind when using this type of equipment. Okay. Now, with that being said, we're going to go ahead and close out the presentation. I hope you enjoyed the presentation and learned something new and useful of what we discussed today. And thank you again for joining us.